Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our honor today to have Yuri Leskovic with us, visiting from Stanford University. Yuri is an assistant professor of computer science at Stanford. We know him as one of our star interns and former MSR fellow. And he's been pursuing a very, very interesting and challenging but rich area of probing large-scale networks, both social communication networks as well as information networks, aspects of the web, understanding the revolution, how information diffuses on these structures, understanding large-scale structure that you can typically only gain insights about through large-scale analyses. Yuri has won numerous awards, even during his graduate work, and I'm sure more to come, given how wonderful and his papers are, and his research and his deep thinking. He's already had 3 Best Paper Awards at Tier 1 conferences. He won the ACM KDD Dissertation Prize, won the KDD Cup in 2003, and I guess he and Andreas and Carlos Gestrin were involved in that was the water networks, right? The Battle of the Sensor Networks. Won the Battle of the Sensor Networks competition in 2007. I see in his CV he says he holds 3 patents. They're all Microsoft patents, I have to say, and he co-chairs the machine learning and data mining track at the upcoming WWW conference. So go ahead, Yuri.
Yeah. Okay. Thanks a lot. So the work I'll be presenting today will basically talk about networks and networks where edges are positive and negative, right? And this is a joint work with Daniel Hutchinlocker and John Kleinberg from Cornell. And we have 2 papers on this. One is coming out at this year CHI, and the other one at WWW. And I'll try to cover both of them, right? So this is basically the idea or the plan for the talk, right? So if you look at how we look at network structures, most of the work usually just focuses on positive edges, right? Meaning friends, followers, things like that, right? I analyze the network where I treat all the edges the same in a sense that they all say something positive to me, right? But generally, edges or links in these networks can be at least, you could sort of classify them at least in 2 classes, right? You could say, okay, some of them can represent some kind of friendship, and the other one can represent something that is the opposite of the friendship, right? And what we want to study is these types of networks, okay? So now, if you say, I want a network where I will have these pluses and minuses, the question is, how can I go infer these pluses and minuses? Where can I get the data, right? And one way is to say that users will express these attitudes, these positive and negative attitudes implicitly. So here's an example, right? So for example, the way how users are using this social networking or online social applications could give me clues on whether that particular connection or action is positive or negative. So for example, product ratings would be one such thing on Amazon, or rating other people's reviews as helpful or not would be one such thing. For example, I'll show you examples of this thing where on Wikipedia you have editors who then go up for promotion to become administrators. And in order to do this, there is a public vote, right? So now a positive edge means I voted positively on your promotion, and negative means I opposed your promotion, right? So this is one. And do you want my power? Okay. So the other way to infer, let's say, the sign of the edge would be through text, right? Or taking the text and trying to do some kind of sentiment analysis. And you could create assigned networks from text. And maybe one way to look at this is this quite well-known picture from Lada Damic and Natalie Glantz, where these are conservative and liberal bloggers, or the other way around, and this is how they link to one another, right? And you see these 2 clusters that don't talk that much. Okay, so that's networks with implicit edges. So what we looked at were networks with explicitly signed edges. So what I mean by that is basically what I want to find data that is relatively large and where every edge is naturally signed, right? So I want a graph like that, right? So on every edge, I'll sort of have a positive edge, positive sign or a negative sign. And here are 3 such data sets that I will be talking about, and I will tell you how they are, right? So the first one is this product review website called Epinions. And on Epinions, people write product reviews. And then there is also a social network where you create connections to other people. And for every connection, you have to say, basically, it's like a trust-distrust connection, right? Do I trust this person's product reviews, or I distrust this person's product reviews, right? So here, when a user creates a connection, they have to either put a +1, meaning I trust this person, or a -1, I don't trust this person. Okay, so this is given. It's not something that I'm inferring, but user is telling me, do they trust it or not? The reason why this social network is then used is that these trust-distrust relations are then used for for the rating of the product reviews, right? And the more trustworthy you are, the higher your product reviews are rated. More people see your product reviews, and Epinions gives you more money. So Epinions is actually sharing its revenues with the people who write these reviews. So it's important that you get a lot of trust edges. Okay, so that's one. The second one is this Wikipedia that I was telling you about, where I have this voting network where that is completely public. There is a public record of how people voted, and here a signed edge means, was I in favor or was I against someone becoming an administrator, right? This creates an edge to that person, okay? And the last data set that we look at comes from the Slashdot, this online technological blog, where there is a social network associated with that, and you can tag every person as a friend or a foe. And the idea is, do you like the person's comments or not? Okay, so comments to the articles that are posted on this website. Okay, so these are now 3 very different social applications on the web, where all of them have some kind of network behind them, and this network is naturally signed. And users explicitly assign signs to these edges they create. So this is sort of what is in common, but what is different is that, for example, in this case, this is who trusts whom. Here, other people can only see your trust edges, but nobody knows what are your distrust edges, right? The distrust edges are private to yourself, while everyone can see your trust edges. On Wikipedia, it's again very different, because here everything is public, right? And the way how you vote really has some consequence that, can ruin someone's life, if you like, right? And then Slashdot is basically a bunch of geeks, and it's not clear what these things really are, and what does it mean to tag someone as a foe, and so on. Okay, so this is what is similar and what is different. So, okay, now I should tell you what I want. Or before, this is just the quick statistics. So I have between 100,000 and 7,000 people, between almost 1 million and 100,000 edges in these networks, and then the fraction of positive edges is around 80%. Okay, so this is the data that I'll be looking at. Yes?
First 2 networks, it seems like you could also get into a situation where most of the trust-distrust edges are directed towards a small subset of people. And so it's more bipartite. Is that true?
I'll come to all these questions. It's an excellent question. I'll come to exactly this, how bipartite these things are. But it's an excellent question. Okay, so here is so now I told you what the data is. I told you I'll work with signed networks. So what do I want to basically study, right? I want to study how do these signs and the network structure, how do they interact with one another, right? Are these signs basically just sort of randomly scattered across this network, or is there some pattern? And more interestingly, I want to study or evaluate what kind of social theories could explain how this network structure and signs, how do they interact? And the last thing, what I want to do is, can I accurately predict, can I sort of build very toyish machine learning models that will tell me, is there a positive or negative relationship between a pair of people, right? So that's basically the plan for the talk. Okay, so if you now go and say, how could I go about saying, trying to relate network structure with the signs? One basic intuition would be something like this, right? So I could say, a friend of my friend is my friend, right? So if me and Eric are friends and Eric and Paul are friends, then me and Paul are likely to be friends, right? So that's sort of the first thing, right? The second one is saying, enemy of my friend is my enemy, right? Also makes sense. Or, friend of the enemy is also my enemy. Or, enemy of my enemy is my friend, right? So this is something that makes lots of sense, right? And now what this is basically doing is basically telling me about triples of people, right? It's telling me what is the structure, how can I complete how can I infer an edge based on the intermediate person, right? And this goes, so this in social sciences is called the theory of structural balance, goes back to 46 by Haider, and he was the first to reason about these things. So basically what I want to reason now is about triples of connected nodes, right? So this is, so if now I say, okay, here are triples of connected nodes, it turns out I have 4 ways to label them with signs, okay? And then if you remember the previous slide, now I can go and start asking myself about these 4 different triads, right? And I ask about this one, right? So what this one is telling me, is friend of my friend is my friend, right? So everything is good. This one is telling me if I close this one, it's saying enemy of my enemy is my friend, or if I close this one, then I say enemy of my friend is also my enemy, right? So for this reason, I will call these 2 balanced, because this is sort of capturing the friend of a friend is my friend, and this one is capturing the other 3 cases that I showed you on previous slide, right? And then these 2 I will call unbalanced, because they are basically inconsistent with the intuitions that I had on the previous slide, right? So for example, if you think in real life, maintaining such a relationship in your social network will be quite hard for you, right? Because you are a friend with 2 people that don't like one another, right? And here, the theory here is that you have 3 people that don't like one another, so sooner or later, 2 of them will join and go after the 3rd one, right? So that's what structural balance says, right? So now I can go into my network data, and what I would expect, if this is true, is that these things will be I will see more of such structures than what I would see if the world is random, and I would expect to see less of these structures because they are sort of harder to maintain, if you like, in the real data. Okay, so that's the first intuition. The thing is, what is nice about this theory of structural balance is that you can show or the following theorem. Basically, if you say if your network is composed only from balanced triads, meaning if your network is composed only from such structures, then this will happen, right? What sort of Alice was saying, right? Then you can show that your network has to be like this, right? It sort of has to be bipartite in a sense that you have 2 coalitions, right? You have coalitions A and B where you only have positive edges inside each of the 2 coalitions and negative edges crossing the coalitions. Okay? So this is what this balance implies, right? So if my network is composed of balanced triads, basically if my network obeys this friend of my friend is my friend and the other 3 rules, then globally my network will look like that. Okay? So that's the cool thing.
What are the detailed schematic Cartwright Harari? Is this the theorem of the structure? Do they took like parameters too?
No, it's easy, right? If your network has such structures, then you can always put the nodes in 2 sets such that either this will happen, or if you have no negative edges, then you just have a network of positive edges. Okay? But that's basic. The idea is from these local rules, global, you can say something about the global network structure. Yes?
Are you now assuming that the links are undirected?
Sorry? Right now I'm assuming edges are undirected. Yes. So this is saying edges are undirected. Okay? And the way how this was actually developed was if my graph is a complete graph. So everyone has an edge to everyone else, right? And then you'll get something like that. But even like it generalizes even if your graph is not complete. Okay? Okay, so this is this. So let me now tell you about one thing that is sort of a bit more specific, right? So all our data sets or the domains we study, they are naturally directed, right? So one way to apply this theory that I just showed you would be just let's forget edge directions and apply the balance theory and try to see how these signs and edges correspond. There's also a different interpretation of these positive and negative edges that you can sort of trace it back to this paper by Guha et al., where you can say the following thing, right? You say every positive edge basically tells me something about the status of people, right? So if A gives a positive edge to B, this means that B has a higher status than A, right? And if A gives a negative edge to B, this means that B has lower status than A. Okay, so it's not really about friend and foe, but it's about status. How good is someone? This says B is better than A, and this says B is worse than A, whatever, in some kind of status sense, right? So that's another way how these positive and negative edges could appear in networks. Okay, and just a small example, right? So here's A points negatively to X, X points negatively to B. So now I can ask, okay, what do I think this would happen here, right? So what structural balance would say is put a plus here, right? Because we are friends and we have a common enemy. Okay, so enemy of my enemy is my friend, right? While status theory would say A is bigger than X, X is bigger than B, so A is bigger than B. So I should put a minus here according to the status theory, right? So here is balance would say put a plus, status would say put a minus, right? Because status of A is higher than the status of B, right? Just by the transitivity, okay? And the same example the other way around, where now B says B has a plus to X, X has a plus to A. So by balance theory, I would put a plus here because it's all three of us are friends, right? If I put a minus, this says there is a person who has two friends that don't like one another, and we said that is bad before. So balance would put a plus here, and status would put a minus, right? Why? Because again, X is bigger than B, A is bigger than X, so A is bigger than B, right? So A looks down on B. Right, so that would be the prediction of the status theory, right? And what I want to do for the rest of the talk is sort of go reason about these things and see how do people create these edges, right? Because these are two fundamentally different ways of how people assign edges here. Okay, so that's yes.
I can imagine an extended balance theory where you have larger structures that are stable.
Sure. Yes. So it's a good point. So.
By those structures that would hold, so kind of like scaffolding that would hold friendships in place even if two people were enemies, and learn those scaffolds. I will show you a bit about this, but one way how to generalize sort of to larger structures is just to say I want these larger structures to have the product of the signs has to be positive, right? So it's a minus times plus, right? That's a positive thing. So that's the way how you generalize to sort of bigger structures. Okay, so that's what I want to do. So for the rest of the talk, basically I want to look at how do these two theories of status and balance, how do they align with this network data. I don't just want to tell you sort of which one is right, but I want to go into a bit more detail and how these theories are reflected in the data and compare them. And why do I want to do this? Because if you give me insights how these linking systems, how people use these linking systems, right? Because nobody tells them, this is about status, this is about balance. It's about, is this a friend or a foe, or do you like this person to become an administrator or not, or do you like this person's reviews, right? So I want to see if these theories say anything about how are we using these these systems. And the other thing is that basically, as far as we know, this is one of the first things that actually looked at networks that are signed that are a bit bigger, okay? So that's the plan. So first, I want to show you about the balanced case. So I'm evaluating structural balance. I'm considering my network to be undirected. And so what is this big table showing me? So I have the three data sets. I have the probability of a particular triad. So each row here is a particular triad. I'll show you that. This is the fraction of those triads in the network, right? So these numbers should sum to 1. And this is the fraction of such triads in the network if I would randomly assign pluses and minuses to the network. Right? So I keep the network stable. I keep the total number of pluses and minuses the same. I just sort of shuffle them across on the network. Right? So this is sort of what the proportion of the triads if the signs would be randomly distributed on the network. By keeping the proportion. Okay. So the first one, right? This is the stable, the balanced triad, right? And I see it much more than what I would expect to see it by chance, right? So balance gives me a good prediction. Then this is the second balance, right? Two friends with a common enemy, and I see it more expressed. Actually, all this is statistically significant. The only place where this is not more expressed is in /dot. So here I sort of put almost a check mark. Okay, and then this will be now the two unbalanced cases. And again, for example, this means I have two friends who don't like one another. I see this much less than what I would see by chance here. Okay, so again, this triad is much less expressed than what I would think if the world would be random. Okay, so that's good. And this is now the last one, all three minuses. And actually, this one is more expressed than what I would expect, right? So there are more triples of enemies than what chance would tell me.
Okay, so this sort of is inconsistent with the balance theory. So this is now if I think about balance. So now I can go and try. So here I just threw away directions of the edges. So one way to go now would be to think about, OK, what if I also try to consider directions of the edges? So now I will change the setting a bit, and I will be thinking about evolving directed networks. OK, so here is what I want to do, right? So I want to think about directed networks where now I can go and again ask, OK, how many of these directed triangles are explained by balance? So here are the 16 possible directed signed triangles, right? So why 16? Because for each of these two edges, I have to decide the direction, and I have to set to have the sign. So it's 2 times 2 times 2 times 2, so it's 16. And this is now the edge that will occur, right? So the setting now is this node is creating an edge to this node. This is the context in which they created. There are sort of 16 different contexts, right? And now if I use my structural balance theory, the way it is suggested is forget about the direction of the edge and start predicting, right? So in this case, I would predict a plus, right? So this is what balance would say. And now I can go in the data and say, is this directed thing more expressed or less than what I see in the data? And I would find that it is. So then a second here, I would put a minus, right? I have a plus, a minus, so I would put another minus here, right? These are now the predictions by the balance theory, right? So makes sense, right? And now I can go into the data and start checking how many of these predictions are correct. And it turns out that only half of them are correct. So what I mean by that is, for example, this thing is overrepresented in the data, meaning this is a stable triad now, and it occurs more often than what I would expect. But for example, some other one, for example, this one is underrepresented, right? So it turns out that when you have two minuses going this way, people like to put a minus here, not a plus. Or here's another example, right? Where I have pluses going this way, then people like to put a minus here, not a plus, right? Which seems to be something that aligns well with the status theory, right? So it says, you are better, so yes, I'm better than you. Okay, so at least if you look at the data, here are two examples, for example, where status theory makes mistakes. And these are the other cases where status theory gives you wrong predictions.
So one could also imagine balance theory being extended a little bit. You want to fold in notions of separating out the actual reality of plus minus from communicative intent. It might turn out that you're more stable to have a friend not like people who are friends, or vice versa, if you don't communicate it. And so it'll be a bias to not express in the graph the information, but it's true in reality. So you can dig into much of these things and come up with stories that involve extra network or non-communicative intention.
So I agree that there is all these edges that are not present, right? Or sort of all these evaluations that people maybe are not willing to give because there is some cost to doing this.
Bias distribution there's certain biases to which they're not given. It's not a random deletion of marks. But
I agree with what you say. On the other hand, for example, you can imagine on Wikipedia, right? It's very costly to say, yes, I oppose you, right? Because everyone else sees that, right? So there you could say people really give it if they feel strongly about it. For example, on Epinions, nobody sees who you distrust. So in principle, you could go and just distrust everyone else, and nobody will look you sort of. So if these two things are similar, so if the results from Epinions and Wikipedia will be similar, then maybe that will answer your question. Okay, so.
Where do you get the negative edges in places where they're not public? So.
Sorry?
In places where they're not public, where did you get the data for the negative?
From the database, from Epinions. So I was able to crawl Wikipedia, I was able to crawl /dot, but I had to get the data from Epinions.
With permission, basically.
With permission, yes, from them, right? You can't obtain it through the web interface. Correct. Okay, so 8 out of 16. The question is, can we do better, or can the status theory do better? And now the answer is yes, and now let me tell you about this status theory. Okay, so here is how we'll think now. So all my edges are directed, and edges are created over time. So I'll be still reasoning about triples of nodes, and the way I will be reasoning is, X creates some edges, and now node A evaluates node B. Okay, So this is what I would like to figure out now. And what I'll be saying is, what can I say about the behavior of this edge given the signs that the x gave? Okay, so I want to sort of consider what happens here in the context of x, right? X is giving me the context. What I mean by that is x context means what are the directions of these two edges and what are the signs on these two edges, right? And I would like to know how does this sign A and B depend on what x did before, okay? And the point here is basically that instead of studying this as an independent event, now I will sort of condition on the action of x, right? I will say x did this particular thing. Now A evaluated B. What can I say about the behavior of A? Okay? So that's the idea, right? These edges are embedded, so I have this context. Okay? And the same 16 triads as I showed you before, these are now the 16 different contexts, right? So this is the edge that gets created, and here's the node x, and this is the context, right? So it's direction and the signs. And here are the 16 different contexts. Okay, and I'll call this now contextualized links, right? Because this red link that occurs is put in this particular context. Okay, so that's how I will look at this. And now I need to make a few definitions. So first thing is that different users make signs, sort of give signs, or the proportion of signs they give is different, right? So I will define what I call a generative baseline of a user U is just the fraction of pluses the user U gave, right? Sort of this is how positive are they on the average, if you like, okay? And then I have something that I call a receptive baseline, which again says how many pluses they received. Okay, so it's, you know, how popular are they in some sense. Okay, so these are the baselines. So I'll just take a node and count what fraction of things that people point to them were positive, and then what fraction of edges that they give were positive. Okay, and these are the baselines. Okay, and now what I want to know is how does your baseline, or how does your behavior change from the baseline based on the context, right? So if I know what x did, how will your behavior change from this baseline behavior? Okay, so what is important to note here is that I'm not interested in modeling what will you do, but I want to model how will your behavior change from this baseline behavior. Okay, and the measure that I'll introduce, we call it surprise, and basically it will be something that will tell me how much does the user behavior deviate from the baseline when they are in this particular context T. Okay, so I want to characterize how much does the behavior deviate from the baseline. So the idea is, what do you tend to do in this? What does A tend to do in this situation versus what does A do when I don't care about directions and signs here? Okay, so I want to know how does the behavior of A change in sort of in this context versus overall possible context. Okay, so here's how I compute things, right? So let this be all the instances of a particular contextualized link T. So basically the idea is if this is the contextualized link, now I take all pairs of people that participate in such a, or all pairs of edges that participate in such a structure, and then what is the baseline context is just generative baseline for this context is just the sum of generative baselines of all nodes A, which is basically what is the expected number of pluses I would see in this context if everyone would be behaving based on their baseline. And again, the receptive baseline for T is the sum of the receptive baselines of these guys here, right? So again, is what is my expected number of pluses that would occur in this particular case? Okay, so this is if people would be behaving independent of the context. So now what I define as a surprise is basically I also count how many positive edges I really see in this case, and then I want to quantify how far away is the observed thing from the expectation. So I will be measuring basically the number of standard deviations by which the number of positive links differs from the generative baseline that I defined here. And similarly, I have a receptive surprise, which is again just the number of standard deviations that positive links deviates from the receptive baselines, right? So I'm quantifying how much deviation is there from what I expect and what I see. And the unit the unit in which I measure this is standard deviations. Okay? So if the surprise is positive, this means I see more positive links than what I expect. If surprise is negative, then I see less positive links than what I expect. If these surprise values are around 6, this means they are 6 sigmas away from the expectation. So everything that has surprise more than 6 is super significant. Okay, so let me now show you 2 examples. I think I showed them. Here they are, right? So this is the first example, right? So here's x. This is now the context, 2 negative edges, one pointing up, one pointing this way, and I want to reason what would happen here, right? So what I expect here is this is the following, right? So I expect A to be more negative than generative baseline of A, right? Why? Because A is the highest status, so A will be, and this is the low status. So if my status theory is correct, A will be more negative than what A usually is. And if I now ask, OK, what is the receptive baseline? So if I look from viewpoint of B, because B is low status, he's more likely to receive a minus than he's to receive a plus, right? So also, like this is the surprise should be more negative than the receptive baseline of B, right? So the generative of A should be negative, and and receptive of B should be negative. Okay, so they should both be more negative than what they usually are, right? So from the viewpoint of A is more negative than what they usually are. From the viewpoint of B, they are more likely to get a negative edge than what they usually get. Why? Because A is high status. Okay, and here's the same example flipped around, where I would expect the same thing. So now what I would, I think I should be flipping this around, right? Because what I want to say is so imagine that this edge is flipped around, right? So B is the highest, B is the lowest status, and then A is the highest status, right? So if it would be evaluated this way, B is more likely to give a plus, so surprise should be positive, and because A is high status, he should be more likely to receive this plus. Okay, so these are 2 basic examples. But here's a different example that will show why this thing is a bit complicated, right? So let's consider this what we call joint positive endorsement, right? So I'm considering this type of case, right? So there is an X could give pluses to A and B, okay? And now I want to figure out what will happen here. And what we see in our data is the following. We see that A is more likely to be positive than the baseline. So generative surprise of A is positive, meaning A is more positive than usual. But receptive surprise of B is negative. So this should be negative. So what this means is that for B, this edge is more negative than what B usually gets. Okay, so in some sense, I almost get like a contradiction. Here I'm saying A is more positive than usual, and here I'm saying B sees this action more negative than usual. Yes?
Which one's A and which one's B?
Because I have the direction of the edge.
Oh, I see.
Okay, so A is the guy who's giving the edge, B is the guy who's receiving an edge. Okay? And now let me give you a story and tell you how this is consistent. Okay? So here's the story. Okay, so think of a soccer team. Now I can create a signed network on the soccer team to ask every person, how does your skill relate to the skill of some other person, right? And if that skill, so this way I can build a signed directed network where I will put pluses to people who are better than me, and I will put minuses to people that are worse than me, right? And this gives me a network. So I assume there is some ordering on the skill set, the skill of the players. I ask every player who is better than you, who's worse than you. This gives me like a signed network, right? And now imagine that I haven't yet asked yet what A thinks about B. All I know is what X thinks about the 2 of them, right? And now the question is, what can I infer about A and B from basically the information that X gave me about them? Okay, so that's the setting, right? So what can I infer about the answer of A? And okay, back to so here is what I can infer. So here's the first inference is that I can think this way. I can say, because B has a positive incoming edge, B is high status, B is a good soccer player, right? So then evaluation of A should more likely to be positive than if A would be evaluating a random guy, okay? So here's a small picture, right? So if this is the whole span of here is the best player, here's the worst player, right? The average player is here in between, right? Because B got a plus, it means B is better than average. So B is somewhere here, right? And now A says, okay, how will A evaluate B? Yes, he's more likely to be positive than what he is to a random guy. Okay, that is all what this is saying. Because B got plus, B is a good player, so yes, A will be more positive than what A would be compared to the baseline when sort of he's comparing an average player. Okay, so this is from the generative side of things. Okay, so now this is now from the receptive side of things. How B will see this, right? B sees the following thing. B says, okay, because A has a positive edge, A is a good player, right? So the evaluation A will give to me will less likely be positive than what I would get from a random guy. Okay? So again, the same picture, right? So here's the average player or the baseline. I know A is better than average, so A is here. And now B, it doesn't matter where on this axis B is less likely to receive a positive edge from this one than from this one, right? So from this point of view, from the point of view of the receiver of the edge, he will see this action to be less likely to be positive than what they would get from a random guy. Okay? So that's the story how basically you can get different predictions based on the viewpoint, based on where do you look. Do you look at the edge from the point of the receiver or from the sender of the recommendation? Okay, so now I have to tell you how this status theory will make predictions. So here's the idea, right? So I will assign X to have a status of 0, and then when if X points positively to A, I will assign U status of 1. Otherwise, I will assign a status of -1, and if the edge is in the other direction, then I can sort of turn the direction of the edge and turn the direction of the sign, right? So plus this way means minus that way, okay? And so in this case, both A and B would have status of 1, okay? They are both better than X, so that's why they have status of 1. And then now I need to say, okay, how is this surprise value, this deviation from the baseline, when is it consistent with status? And here are the two rules. From the generative side of things, right, from the viewpoint of A, then this is how I think. I say the status of B has to have the same sign as generative surprise of A. Basically, it says if B is high status, A should be more positive. If B is low status, A should be more negative than what they usually are. Okay, so this is what this is saying. And then from the receptive side, from the viewpoint of B, I'm saying the status of A should have the opposite sign as the receptive surprise, right? So I'm saying if I'm B and I'm high status, then, if I'm B and A is high status, that means I'm more likely to receive a minus. And if A is low status, I'm more likely to receive a plus from someone who's below me. And if A is up, I'm likely to receive a minus, right? So here I get the difference in the signs. Here I get the same signs. Okay, so this is how the whole thing works. So right in this case, this is what I would expect, right? So the generative surprise of A has to be positive, and the receptive surprise of B has to be negative, right? They both have signs of 1. So in order for this to be consistent, I have to have equal sign here. So I have to have plus here, and I have to have a different sign, so I have to have minus here. Okay, so now here's a huge table with results, right? So bear with me, and I'll explain it nicely. Okay, so these are all the 16 different triads. This is the number of times this triad occurs. This is probability that the triad is closed with a plus. Remember, baseline is about 80%. And then these are my surprise values, right? This is the number of standard deviations the behavior deviates from the baseline. Minus means, 50 standard deviations more negative than what expected. And plus means this many standard deviations more positive than what expected, okay? And then, so these are the numbers. And here are sort of the predictions. These are the predictions from structural balance. These are the predictions based on the status theory, okay? So let me show you one example. So here are now the 16 things that I have. So for example, if I take this particular triad, this is 11. I can go to line 11 here, right? I see that A is more negative than what they usually are, and B sees this more negatively than they usually are, right? So the generative surprise of A is negative, and the receptive surprise of B is negative, right? And this is opposite of what balance would say. The balance would say they both have to be positive, while our theory says that they should both be negative, right? So why? Because balance says here's a plus, so here should be a plus, right? So they should both be more positive than what they usually are. What I see from here is that they are, from here, that they are both more negative than what they usually are, right? So this gets closed by a minus. So this is something that the status says, but balance doesn't say, okay? So do people see that, right? So what this is saying is B is greater than X is greater than A, so what is going this way, it should be, wow, wrong. What is going this way, it should be, I should give a minus this way, right? Because this is the lowest guy, this is the highest guy, right? So this way should be the minus, which is against what balance says, but it is what turns out in the data, right? So my status theory gives me the right prediction, this gives me the wrong prediction. And the point that I made before was balance gives me around 7 or 8 of these things correctly. Status gives me 13 or 14 of these things correctly. Okay, so this is one example, and here's another example that I was showing you before, right? It's this way. So what this says is that this says that B is less than A. So status would say put a minus here. Balance would say put a plus, right? It would say two friends with a common enemy. And if you go to this particular line here, again, you would find that people put minus in this example, right? They behave more like the status theory and not as a balance theory. Okay. And then the last thing that I want to show you is, okay, what are the mistakes?
So you're just trying to get the semantics of status in the applications you're looking at. So status, like soccer playing ability, to apply to necessarily to opinions. And so what's the mapping to the semantics there?
That's a very good question, right? So for example, the last slide I will show you is how, like, for example, voting on Wikipedia, right? Why should voting be about status? There should be some bar, and if you are above that bar, you are above the administrator bar, and if you are below administrator bar. But then if you look how people, I'll basically show you the slide where I have some kind of proxy for status and how people vote based on the difference in status. Okay, so wait, but yeah, I mean, it's a good question. Why should there be status if these things are not about status? They are about opinions or preferences or trust, right? And there is no inherent status in there. So, but basically what is my point is that in these systems, people behave like they are assessing status of one another and not necessarily using this friend of a friend type reasoning.
And you can imagine a model mixture with parameter, right?
Of both examples. Yes, exactly. So I'll come to that. Okay. Okay. So here are the four different mistakes that I'm making, right? So this one and this one are the T3 and T15, and the red two are 2 and 14, and then this is the last mistake. What is there to note is that all these examples up here are basically just variants of the same thing, right? So I can get from this triad to this by flipping the direction here and flipping the sign, and I'm in this case, right? So if you look at all these examples, they are all the same example at the end from the status point of view, right? They are all telling me the same thing, right? Because these two pluses here, I can flip them around and make minuses, and I'm at this case, right? It's again telling me X is the best, and A and B are worse than X, right? So from this point of view, these are the mistakes that that I'm making here, and this last mistake is the case where balance does well, right? It's like I should be putting a plus here while what I'm predicting is a minus. Okay, so these are sort of the 5 mistakes I'm making. So going to the Eric's question, now the question is, for example, the following. So I told you this status, so what does status tell me about reciprocation, right? So so A creates an edge to B, now B has to create an edge backward, right? If my status theory is correct, then B should be negative, right? Because B is greater than A, so this way should be a negative edge, right? Similarly this way, right? There should be a plus here. So the question is, when people reciprocate, do they obey this theory that I was saying, or the balance, right? Based on the balance, the edge should have the same sign. So if I'm friend, I should be a friend back. In the status theory, the edge should have a different sign. And basically what I'm interested in is what is the sign of this edge given that the first edge was positive or that it was negative. And if I look at this, basically what I find is that basically this reciprocation is strongly follows balance, right? So people are more likely to reply with the same sign than they are reply with a different sign. And here the point is also that all these then depend, right? So the strongest signal is just reciprocation. The second, and then what you get is all these triadic effects, right? What you also find then is from the balance point of view is that people are more likely to reverse the sign if they participate in an unbalanced triad, right? So you could say, if I'm in an unbalanced triad, am I more likely to try to make this triad become balanced? And that is something that happens in the data. Okay? So going to question that Alice had at the first thing is, how does this global network structure interact with the links, right? So now I want to understand how does this network globally look like from this pluses and minuses point of view. And let me skip a bit. So here is what I want to say, right? So basically, both theories make predictions about the global network structure, right? For structural balance, I already showed you, right? This tells me that there will be coalitions in my network, right? So my network will look something like that, right? Pluses, pluses, and minuses across. What status theory says me that there should be like a global status, meaning that I should be able to assign every node a number such that positive edges only point from nodes with low number to the high number, and negative edges point the other way around, right? And now I can go into the data and look, is globally my network more like this or more like that? And to sort of scare you with a big table, this is what's going on. So this is like the fraction of nodes that obey the balance criterion, and this is a fraction of nodes that obey the status criterion. So yes, it's less, but here are two ways how I can make my data random. So here the idea is, what if I randomly assign the signs in my network, and you can see that then the network is more bipartite than what it is in reality, right? While if I make my network random, it obeys status less than what it obeys in the reality, right? So what this basically tells me is that globally networks obey status more than what they obey balance, right? So even globally, status is more expressed than, or there's more evidence for the status theory than there is for balance theory. Okay, and then the last thing. So now I showed you these two theories. One thing that I want to do next is to say, okay, can I go, given the signs of the edges, can I sort of hide the sign of an edge and try to predict it? Okay, so given how this edge is embedded and what are the signs of the edges adjacent to this particular edge, can I figure out what should I predict here? And so the way I will go do this is very simple, right? So for every edge, I will create a feature vector, and this feature vector will just count the types of triads this edge is embedded in, and then I'll train a logistic regression classifier. Okay? So here are the 16 features that I will be using, right? So if I want to predict this edge, then I will count how often does it occur in this context, in this context, in this context, and so on, right? And I have a feature vector of length 16. And here's the example of the logistic regression. So I subsampled my data so that random would give me 50%. And the point is that using these 16 features, I can predict almost like with 90% classification accuracy, right? So with basically between 80 and 90% classification accuracy, I can predict whether a particular edge will be positive or negative. Okay, so that's basically the first point here. And let me show you the last thing, right? So the last thing that I want to then ask is, okay, if I can do this with 90%, I also know that all these applications are very different. So what I want to ask then is to say, okay, what if I would train my model on Epinions, where people rate product reviews, and then use this model to predict how people will vote on Wikipedia, right? Can I do that? Okay. So the idea is I will train on /dot, and I will predict how people trust each other on Epinions. And if I do this, here's what this table is showing me. So I'm training on the row data set, and I'm evaluating on the column data set. Okay? So if you look at, let's say, the first line, right? So when I train on Epinions and I evaluate on Epinions, I do best, right? But even if I evaluate the Epinions model on /dot or on Wikipedia, I do almost as good as if I evaluate if I train the model on /dot or if I train the model on Wikipedia, right? So what is the point? The point is that these models have like amazing generalization performance, right? So I get almost the same performance on Wikipedia regardless what I use for training. Or on /dot, I do about the same regardless of whether I use the /dot data set to infer how people create signs or if I use Epinions or Wikipedia. And similarly here, right? I lose about 1% in classification accuracy, right? And what this is basically telling me that even in these very different applications where people vote and everything is public, and here where only positive stuff is public and nobody sees the negative stuff, the model is the same, right? The model does as well regardless of what's the application that I trained it on.
Did you do an analysis of the future weights and see what kind of features you have that are discriminative? Which one of the 16 are really the discriminative one?
Yes, I skipped these slides.
What's the aim? You can tell me from your memory.
So it turns out that let me tell you offline, okay? Okay. So this is the first. So what is the surprising result here is that regardless on which data set I train, I can do as well as on the test data set as if I train on itself. Yes?
But how do you explain the variation between the columns? As why is Wikipedia so much less predictable than Epinions and /dot?
That's a great question. I don't have a good answer, but the point is exactly as you say, right? It just seems that yes, Wikipedia is like a harder problem than what Epinions and /dot are, right? Like, because I always do worse. And I noticed that regardless of sort of what kind of model I was using, the performance on Wikipedia was worse. Now, why is that?
This theory does not apply as well?
No, so here I was using also, like, I skipped a few things. So let me, I can go back if you like. So one thing is that when I do this logistic regression, right, I can train these coefficients, or I can take these coefficients directly from the theory, right? So for example, I can apply the balance theory and say, this is the coefficients, the logistic regression coefficients balance theory would say, right? It says, if this is the edge I'm interested in predicting, if it's embedded in a plus plus or embedded in a minus minus, put a plus, right? So I put ones here. If my edge is embedded in such cases, then put a minus here, right? Because these are unbalanced cases. So I would put a minuses here, right? And now what I'm showing you here is, so for example, this is coefficients that the theory suggests, and these are the learned coefficients, okay? And you see that the signs are correct, right? The only case where it's not correct is this minus minus, which is the all minus triads, which we also saw that people put minuses there, right? And similarly for status theory, I can compare what does the handcrafted logistic regression model do, and what are the learned coefficients. And the slide that I also skipped is the following, right? So here's the point. For example, this is the deterministic balance, so where I set these logistic regression coefficients by hand, and this is where I set them by learning, right? And you see that I gain sort of very little. That's a good question. So the different color bars are how well embedded is the edge. Okay, so how rich is my feature vector, right? The more embedded, so this 25 means that the edge participates at minimum in 25 different triads. So my feature counts are very good. While here at 0, most of the features will be near 0 because most of the edges won't participate in many triangles. So it was just to see how much of this effect is there. But what's the point of this slide is that, so when I have a det here, this means deterministic. So this is like I set coefficients by hand, either +1 or -1. And when I have learn, this means that I learn the coefficients, right? And the point is that there is not much difference between deterministic and what I learn. So even these theories do well. And now you can go and compare sort of the status theory, predictions from the status theory, and the balance theory, right? So this is the deterministic balance, this is deterministic status. And for example, up here and also up there, status does a bit worse in terms of predicting than balance does.
The opinions and the slashdot is something that's based on less information, and people give less thought to that than Wikipedia. And Wikipedia people, take very seriously and see it as their life's mission, and hence it's harder to predict based on this kind of superficial.
That could be an explanation. So the last slide that goes to the Eric's question is the following, right? So how do people vote on Wikipedia? Okay. So what am I asking here is how likely am I to vote on someone positively? And here I'm having some notion of status. Okay, so I'll tell you what exactly this means. But here it will be when A and B have about the same status. Here when A has lower status than B, and here when A has a higher status on B, right? And A is evaluating B. Okay, so here is what I see, right? So here is now probability of voting positively versus the difference in status. And for example, one way to quantify status on Wikipedia is to say how many edits have you made, right? And what this says is the following. When B, so the guy who's up for administrator, made many more edits than A is very likely to be positive, more positive than the baseline. When they made about the same number of edits, A is the most negative. And when A has made much more edits than B, again, A is more likely to be positive. And here's a different way a different way to think about status. On Wikipedia, people can give one another these barn stars, which just means that I come to some user, I edit his page, and I say, I give you a barn star. I just, put some image there. That's called a barn star. So now I can say the number of barn stars is the value of your status, right? And here I'm now plotting the barn star difference. And I see the same behavior, right? When A is evaluating someone who's clearly better than what they are very positive about it. When they evaluate someone who's clearly worse than what they are are here. But when they evaluate someone who's exactly of the same status, they are the most negative, right? So both these curves, if I sort of emphasize, have the same shape, right? They are very positive. They get the most negative when A and B are about the same status, and then they sort of bounce back. Both in terms, if you look at the status in terms of edits, or if you look at the status in terms of barn star difference, right? And I guess this is something that we'd also see a lot in conference reviewing, right? If I review from someone who's sort of the same as me, I'm the most critical. If I review from someone very senior or something, I'm generous. And if I review someone who's clearly not at my level, I'm again generous, right? And this is the baseline. So what this again says is that, at least in Wikipedia, right, it's not that there would be a bar, are you good enough for administrator or not? It's basically people tend to evaluate other people based on their own, by comparing them to themselves, right? So what this shows is that it's the relative assessment that matters and not absolute assessment, at least on Wikipedia, right? And these are just two different proxies for the status, but you get the same thing in both cases, right? Very positive, the most critical when we are the same status, and then this bouncing back, okay? So that's all that I wanted to say. So basically, what was I telling you, right? So I was telling you how does the network structure and the science, how do they interact? I was showing you some examples of the structural balance theory that is present if you look at the relations as undirected. And then I also showed you this status theory that can sort of give you very interesting predictions about behavior of the people. And it explains my data much better. And also at the global level, this theory is more, the global structure of the network more obeys the status than the structural balance theory. And then the other two things that I think were interesting, first one is this, that you can basically, with very simple models, you can predict with almost 90% classification accuracy whether the edge will be positive or negative just based on the other edges in the network. That another interesting point is that these models had basically amazing generalization performance, meaning that even though I have these 3 very different data sets with 3 very different applications and very different mechanisms of how these edges are generated, at the end, the same models seem to apply. And one thing that I haven't talked much about is even if you do link prediction, it's good to know who your enemies are. So even if you want to predict whether there will be just an edge, regardless of the sign, it's good to know what are the negative edges. OK, so this concludes my talk. I would be very happy to take questions. Yes?
What are your thoughts about applying these ideas to citation databases?
Oh, wow. So the question there is, how could I get at least a bit of label data, right? If I want to do these predictions, I would want to have a bit of label data. But yeah, you could think that there are citations that I make willingly and there are citations that I make unwillingly. So it would be interesting to see what happens there.
For example, there might be a way to figure out what are some classic papers that most people refer to that some people don't as a proxy for a negative link.
So like this point that you're opening, I think is also very interesting. The question is, there are all these links that are not there, right? Are they like, I'm not in fight with everyone on Facebook that I'm not connected to, right? I'm not in fight with 400 million people and, with 600 I'm friend with, right? So the question is, when does the missing information mean I just haven't expressed my opinion versus, no, I really don't like you, right? So I think that's
people on Facebook who have many shared friends but no link between them for 2 years. What does that mean?
That could, yeah, no, I agree. So it's a good point, yes.
Just if you did follow up what Eric was suggesting, there's research done by Simone and Teufel in Cambridge on, it's called argumentative zoning. And she has done a citation analysis of when you positively cite someone versus when you negatively cite someone. So she would be able to
there's actual
some
data on
label
the
data.
Wow, cool, okay, thanks.
There are many papers who get lots of citations because they have a mistake and many people rush to correct it.
The negative link.
Right. But you have to be able to see that in the content. One other quick thing there, you had the preponderance of triple minuses, the initial part, and there's another kind of theory about that which I wondered if you had looked at, which is the fighting in the mud theory. You see 2 people fighting in the mud, and maybe one of them is completely at fault. He pulled the other one to the mud. The other one is just trying to get out. But if you were asked to express your opinion about these 2 people, all you saw were 2 people fighting in the mud, and you have a negative opinion. And you have this in some forums where you have, say, 2 people on Slashdot who have been exchanging snipes for a long time and get more and more bitter towards each other. You join the network late, and all you see are these 2 very negative people fighting. Maybe one is, and you just give them both negative signs because you don't like their negativity.
That's a good point. So here's one thing. So this is another slide that I skipped. But basically, one thing that none of these theories explain is the following example, right? So what I'm asking here now, I'm saying embeddedness of an edge is just the number of triads an edge participates in, right? And what I'm showing you here, for example, Epinions in Wikipedia is if my edges would be random, then fraction of positive edges that are embedded as a function of their embeddedness would be constant, right? What I find is that when an edge has less friends in common, it's more likely to be negative, and when an edge has many friends in common, it's more likely to be positive, right? So this is something that says that if 2 people like one, or it's much less costly for me to add a negative edge to someone to whom I don't have any friends in common versus to whom I have friends in common, right? And you can also see that, for example, in Wikipedia, this is much more expressed than on Epinions, right? What this basically says is that it's not so much consequence of the balance, but it's basically this consequence of social capital and embeddedness, right? That these negative edges are easy to give to people that you sort of don't have anything in common with, right? And you keep positive edges more close together. And similarly, the way you were suggesting it is to say, yes, if I see a negative fight here, then I just say, I don't like negative. I push it away. And yeah, that's probably also the reason, especially on the web, there's no problem with three people being enemies with one another, right? While, for example, if you study international relations, there you have to have an opinion about everyone, so these minuses are less expressed. But I think it's a good way to think about it.
Imagine a recommendation engine someday running on these sites where you're ready to say something or do something, but not accept a friend, and it gives you a kind of overlay of what the implications are. If you accept that friend, what it says about the pluses and minuses across your network, who you like and don't like so much anymore.
No, that's a good thought, right? Basically, it would tell you, oh, if you don't accept this friendship, you'll make enemies with all these people.
The delta's a little bit down here and so on. Yeah.
This seems to relate to things like Reddit would be a good example, where you're actually in a competition to upvote things. Getting something upvoted enough gets it into the front page. So strategies people will take is that they say to like submit things, you upvote, then anyone who votes up your vote, you go to their link and you upvote it too. So you start working in coalitions to create a critical mass of upvoting of popularity. And there's not a reciprocal thing on the negative side. There's no reason to just downvote people into oblivion. There's one small example that there's some people, it's been said, it's anecdotal, I don't know if anyone's ever looked at it, but that sometimes, because you can look at someone's history in Reddit, and you can see all the comments they voted on, and you can actually vote in their history. So sometimes people will, when someone leaves a snarky remark on their comment, they'll go into their profile and downvote all of their comments for everything, just without any kind of sense or reason to it, simply as sort of a malicious
retaliation
against them.
Retaliation,
And it seems like Reddit is very social, whereas these are different. They have different motivations, so it might be an interesting.
So I spent lots of work on trying to find coalitions in Wikipedia. So the idea would be, are there these sets of people who all vote positively on one another and they don't like that set of people? And we found very little like.
Well, what's the motivation? Wikipedia, what's the motivation to like upvoting everybody around you or approving of them in some way? Like Reddit has essentially a daily leaderboard where every day it goes through this cycle where it's like whoever gets the most votes is they get the immediate reward for having been well embedded in the network and having this kind of activity.
Okay, so I agree. So that would be an interesting thing to study. I don't maybe we would see the same thing, especially on the positive reinforcement side. Even though, on Wikipedia, I want people who think like me, right? I want enforce these editorial policies versus those and so on. So you would think there would be some fighting going on.
How often do the admin votes go on? Does this happen at a regular point of time? Or?
Yeah, we have we had 2,500 elections from, I think, 2003 or 2004 to 2008. So we have 2,500 or almost 3,000 elections. Half of them ended up with a promotion. Half of them ended up without a promotion. And then yes, you can I haven't talked about this, but you can study how do people make decisions, right? There is this person they have to decide on, and there is this now collective decision-making process, right? People come and say yes, no, right? So basically, you can think you have people in a room. You say, what do you think about this? Let's now figure out do we accept this person or not, right? So you can study how does the outcome of the election change as people express their opinions and so on. So we also looked at that, but that's. Oh yeah, anyone can vote. Mostly admins vote, but anyone can vote. So you also find you find people that vote in 400 different elections and so on. So you find people that vote in many different elections. Okay. Yeah.
So I'm wondering if you thought about. I'm wondering if you thought about possible. So when you do your study of the network and statistics, did you look into the possible effects of double counting and whether that would result in any biasness? So one question that I started thinking about during your talk was you have the same triad, and I wonder if it generates this, positive, negative, or whatever loop, and whether for violence theory it would generate more negative examples than for status theory.
So,
or maybe other ways of biasness.
For when I was looking at this, I really know when the edges appeared, right? So I was really able to look at it in the evolutionary sense. So I was counting exactly the same triads in both examples, right? I always say, this is what happened and this is the new edge that will happen. What will this new edge be? right? So I wasn't really looking at the static network, but actually the evolving network. So I was
only using that once.
exactly.
Okay.
Exactly. So I didn't use it. Yes, exactly. Yeah. And then whenever, then of course the question is, what do you do with the reciprocated edges? And I think in those cases, I would just take the first edge. And usually the reciprocated edge is of the same sign, so it doesn't really matter. But yeah, we try to be careful about these effects. It's a good point. Okay, thanks a lot.